Welcome to Math 104, Chapter 5.7, where we talk about logistic functions. So logistic functions, if you are not familiar with them, they're going to look a little bit different than the previous ones that we have seen. So when we go to do our projects, do not forget to compare your answers or your graph to logistic functions. Because it does matter as far as what our best fit might come out to be. So logistic functions, we're going to go right into it. Have an equation that says f of x is equal to c over 1 plus a e, right? E is our exponential value to the negative bx. Now, we are going to start to define a couple of them, those that matter. So this C is super important because this is called your limiting value. It's your upper limit, which means you cannot go above this number, right? The upper limit is the highest possible number that you can be. So limit being you can't go past this value. You cannot exceed this value. Now, E is just regular E that we have been using in this section or in this chapter. So it's not a variable. There is a lot going on here, as you can tell. Notice that we do have a negative value here. So don't forget this negative will change the shape of things. Now, X is just our variable. Our variable term. So just be aware, we won't have to be putting together any of these equations like we have in the past. They're just going to be giving these values to us. Now it says this particular A here, what we're going to be calling as the multiplier, when A is greater than 0. So if A is positive, a logistic function will increase when B is also greater than 0. So B is also positive. So we're going to be seeing an increasing trend when B is greater than 0, or when B is less than 0, so when B is negative, we're going to see a decreasing trend. So pretty much, is your graph going to go up or is your graph going to go down? Now, logistic functions, we said, are a little different than the other ones that we have seen and become familiar with, because these are kind of an example of an exponential growth or decay, but they're going to be shaped a little bit differently. It says when growth begins, it goes slowly to start. Then it starts to increase really fast. This is where that exponential pace comes into play. And then finally, it starts to decrease again. Once more, at a rate that is almost 0. So it's going to be fitting this S-shaped curve. So I'm going to show you this curve here. And you can ignore some of the values here. I keep meaning to change this graph that I have on this page. But when the graph begins, we're going to start to increase. We're going to increase slowly, and then we're going to go quickly, and then we're going to taper off. So this is an example when you have your B term is greater than 0. So this is when your graph is going to increase. We can also have another graph, and I'll show you here to the side when we're going to be decreasing. So again, it's going to go in the opposite trend, but this is when B is less than 0. So when B is negative. Now, one thing again, just kind of ignore these values here. We're going to put in some dotted lines, which we have seen before. And I'm going to put in a dotted line here. I told you guys to really ignore these values on the side. We can even ignore the ones down here if that's the case. Okay. So when we go in to fill this, these values in, right? What is your x-intercept, your y-intercepts? Are there any asymptotes? If there are asymptotes, what could they be, right? You can find one of them very easily. The other one, you might not be able to come up with a numerical value, but you can kind of guess as to what it could be as far as what we have seen so far. So see if you can pause and come up with that. And don't worry about the equation. So x-intercept, and x-intercept is where we touch the x-axis. With these dotted lines, doesn't mean even if I can get as close as I can to this x-axis, the dotted line prevents it. What was that dotted line called? Right? These are called asymptotes. So if you're not able to cross this dotted line, you're not able to touch your x-axis. Therefore, we will not have any x-intercepts. Your y-intercept. Y-intercept is anytime we do touch the y-axis. Now, right here, we could say this is perhaps at 0 with how low it is going. However, we can also say this is any time when x is equal to 0. Now, in order to find this, this can shift on any sort of basis. So if we know that x is equal to 0, let's say we plug in a 0 for your x, right? Then what happens to the negative b that's being multiplied by 0? Well, then that just means that this whole thing becomes 0. So right now we have c over 1 plus a e to the 0. So then what is e to the 0? Now, if you don't know what that is, go ahead and plug it into your calculator, pause the video and come back. Well, anything to the 0 power is not 0, but it is 1, which means this whole thing is just a 1. So we have c over 1 plus a times 1, which again, multiplication between 1 doesn't really matter. So we have 0 c over 1 plus a. This is going to be your true y-intercept. This is any time when x is equal to 0. And we can find it easily that way. Or if you're familiar with your calculator and how you find your y-intercept, that is okay as well. This is just an easy tidbit. Now your asymptotes. We said we have 2 asymptotes, 2 of those dotted lines. What is one of them? Perhaps the easier one to follow because these numbers here don't matter so much. This one is probably the easiest one. And because it's a horizontal line, these are all going to be y equals. So if we're right here, what do we think y could be equal to here? Well, we were just talking about your x-intercept not so long ago, and x-intercept is any time where y is equal to 0 and x is equal to a number. In our case, we could be saying that your y here is 0. So this is one of them. Now this could be considered your like lower limit, right? You can't pass your dotted line, your horizontal asymptote. So if we were to just do this again, but for your upper limit, right? We said, hey, there is one here. We can't seem to cross it. That's why it's going to flatten out. So what could this be? Well, this would be our upper limit, our limiting factor, which we set our upper limit. It cannot pass this value, which is C. Now, we don't know what C is in the context of this problem, so we're just going to label C from the equation. So we said C is often called the upper limit, or the limiting value. Because the line y equals C is an asymptote, oh, cannot spell today, and cannot be crossed. Okay, so now let's go ahead and practice punching these graphs in, finding a good graph, and just taking a look at what they look like. So I'll do this first one on a TI-83 or an 84, and then I'll do the other one in Desmos. Now keep in mind what we said about C, and that might help us build our equation, or build our your scales. So with that in mind, let's go ahead and, oops, we're gonna y equals, we got some junk in there. All right, so we have 10,000. And if you wanted, this would be a great place to practice that fractional button, because it does get a little lengthy at times. So we have 10,000 on top, and I would still put parentheses around the bottom. That's just me. I like to be cautious. So you have 1 plus 9999. We have E, which we said in a different lecture, it is right below the log button on the left-hand side if you wanted to use the one with the exponential, or the, oh geez. So we have E to the negative. When you do the negative, it is between your period or your decimal place and enter. And we have 0.99. We have your value here. Close your parentheses, double check that you typed it in correctly. Okay, now I'm just gonna go to this window. I'm actually going to hit zoom 6. You see it there, it's not a great picture. The reason why I hit zoom 6 is I just wanted a standard viewing window that all of your calculators kind of start with. This is an okay one. It does get us started on what to look for. We can see your y-intercept here pretty clearly. That looks great. But I really want to look for that S-shaped curve. So that being said, let's take a look at your values here. Now we said for your X values, we can kind of play around with it as we go, that's what I'm gonna suggest that we do. Because logistic functions, we actually didn't get to define them. Where would they occur in real life? Well, this would be a great example of a growth of a business, or a spread of a virus, or sometimes, not sometimes, or population growth, right? Or decay. So when we're talking about growth of a business, spread of a virus, population growth, can we have any sort of negative values over here to the side? Keep in mind, X meaning we are in negative time, right? Well, growth of a business back when, right? We can't not, you can either start a business or you don't. There's nothing out in space that you haven't created yet. So when you go to pick your minimum, typically you start at 0 and then you work your way up. So to find your X max, we might have to give it a guess. Right now, when we we're looking at your graph, we just kind of went to 10, and that 10 might have to get pushed out a little bit further, which I'm going to let you guys pick your X max. Same thing with your Y minimum. We're going to be starting at 0, your limiting factor, your limiting value below. And let's take a look at your upper limit. Your upper limit being C, 10,000. So that means we cannot go above this 10,000 mark. So does that mean we should stop here at 10,000? No, we definitely want to get above 10,000. We want to sandwich it in, and we definitely want a good enough job where we can see enough space up here to tell that this is where it tapers off. So we don't want to stop at 10,000. So again, perhaps we give it a guess. We want to go higher than 10,000. So probably 15,000 or more. And notice that for your scales, again, I'll let you choose your X scale here, but for your Y scale, since there's a huge difference between 0 and 15,000, be generous on your Y scale. So pick something that's a little bit bigger. So perhaps 1,000 to start. If you like it, great. If you want to change it, that's okay. So if I'm going to go back to my window, we can start at 0 here. If you wanted to get a little bit negative, that is okay as well. Your max, we said, well, let's start at 10. Let's go up by 1 for now. Minimum, we said 0. If you wanted to start a little bit lower than 0, that is okay. We're getting to 15,000. And we're doing 1,000 just to start. Okay, not the best. We don't get that S-shaped curve. We still see our graph, which is good. So let's play around with your X value because we know that our Y value is pretty set. So that just means we might need to change your X max. So let's change it around. Maybe we go up. Yeah, we can stay with 1. There we go. So we were just kind of cut off. So we were seeing this part right here. So we need to make sure we see this nice curve and this S shape. So one more time, our window right here, I'll be recording it on our page. Okay. So with that in mind, see if you can do it again on this next one. I'll be doing this one on Desmos. All right, so we have a scale or one right here. So your limiting value, we definitely want to sandwich that in. If we want this one, we might want to start, well, let's just plug it in and see where we go. The Desmos. Point 2227. There we go. Can use parentheses when we can. 3, 7. Functions. Maybe it's E. There we go. So I'm looking at a tiny screen, so sometimes it's a little hard to see. There we go. Oops. Oh. Okay, so here, come on, graph. Okay, so we can see our graph a little bit to start, and notice that it disappears on my screen, which means we don't panic. We just need to adjust our screen. So if our limiting factor, right, right now is at 92. Let's at least sandwich 92. Let's get above. And I know Desmos, you can just use the plus minus sign to locate it. Lovely, right? But notice that we can also try to build your window. So if we know that at the very top is a 92, we want to go well above it, let's say 120. And let's say for right now, we can still say -6. That's okay. We might want to change it. There is kind of a difference between -6 and 120. So let's say we're going to go up by tens. That is just for our y values. So right there, you can see we have located our graph, so we don't need to panic anymore. However, we do notice that we are not seeing that S shape. So we do kind of see that increase. We see our y-intercept. That is great. So let's get a little further out to the right. So that means that we want to play around with your X max. So your X max right now is at 10. Maybe we go to 20, see how that is. Again, playing around with your scale. For right now, let's do 5. We're getting a little bit better, still not great. I want to see the nice S shape. So we'll play around with it a little bit more. Maybe we are a little bit more generous this time. If 20 wasn't it, maybe we go to 60 or 70. Maybe we increase it a little bit to 10. Okay, we're definitely starting to see the S curve. So we're going in the right direction. Now I want to see where the S starts to flatten out. So let's do another big jump. Let's do 100. Ooh, better. One more. Let's also do 120 then. Okay, so we are seeing a little bit more. Let's do one more. 170. There you go. So right there, you can notice that you have the S shape. It's starting to flatten out as you go up. So I would say this one is an appropriate window. If you wanted to get a little bit lower or to the left a little bit more so that it's more in the center of your screen, that would be all right. But I think this would be a fantastic window. So you have -10 and 170. And if you wanted, you don't have to do a -6. You can start at 0 if you would like. And 1. So we said 10, say, or 0. Let's see, we said 170, 120, and what were our scales? They're both 10. So that is our graph so far. Now let's try an actual example. So we've graphed it. We can certainly do things on our graphing calculator to come up with these answers. So it says, using the data from 1920 and projected to 2020, the expected lifespan at birth of people born in the US can be modeled by the equation where X is the number of years after 1900. What does that mean? So that sentence means when X is equal to, when we're talking about the year 1900, X is really going to be a 0. So when X is equal to 1, we're talking about 1901 and so forth. So when it says A, what is the limiting number? Pause the video, see if you can come up with that value. Our limiting value would be 82.488 would be our limiting value. So we cannot exceed that. Then it says, what is the initial expected lifespan given that X is the number of years after 1900? So the initial lifespan means the original lifespan when X is equal to 0. When X is equal to 0, right? What is Y? So at the very start, what was the initial lifespan? So in order to do this, right, we can either do one of two things. We can put it into your calculator, use your value to come up when x is equal to 0, and figure it out that way, which I will show. Yeah, I'll show it on Desmos. Otherwise, algebraically, we said we can do this when x is equal to 0, 0.816 e to the negative 0.024. And when x is equal to 0, that does not zero this whole thing out. Instead, it just makes it when e is 0, which is equal to 1. So we can algebraically plug this value in to our graphing calculators and come up with that answer. So let's go ahead and do that on this calculator here. We said 2.488 divided by 1 plus 0.816. There we go. So about 45 years old, so 45.4, so that can round us up to 46. So we're well into 46 years of life. I'll also show you how to do it on the graphing calculator. Desmos is pretty easy. It allows you just to punch in your equation, and then your initial locating where x is equal to 0 by tapping your graph and figuring out that y value. Now we are just going to practice punching in your equation. We have 82.488 plus 0.816 negative 0.024. Oh, don't forget your x value. Double check that you have entered in everything correctly. Otherwise, it won't work. Okay. Let's see. Let's change around your window. Let's see, 82. We can just do 100. Oh, let's do 120. So we'll go up by tens. For now, we'll do that. Okay, so notice that we don't have that S shape that we need, so we're going to adjust your window a little bit more. Most likely it is going to be your max, where we're talking about the values from 1920 or 1900 all the way to 2020. So we definitely need to get our X value up rapidly. So let's do something a little bit bigger. Let's do 150. Well, I guess 120 would be fine. Well, 120 would include 2020. So we'll stop there. And let's go up by tens. Okay. So we don't get our S shape, but what I did here is we're talking about the year 1900, right? So our X values are going to start at 1900. And if we're talking about the year 2020, right, that's 100 years plus 20 more. So 120. So our X mins and max should be starting at about 0 and going all the way up to 120. If you wanted to do a little bit of wiggle room, that's okay. In this context, they don't need an S shape. As lovely as that would be, this is what they're kind of expecting. So from here, we're going to say we just need your y-intercept, which in order to locate it, we can say anytime your graph is touching the y-axis or y, I can't talk right now, y-intercept, y-axis, so sorry, which we definitely want to see a little bit further off to the right-hand side for your initial. So let's go in the negatives just briefly. We'll go to -10. Okay, so you can clearly see your y-intercept. So let's go ahead and see if we can get an intersecting value. Let's just say when y is, oh, so sorry. We'll do value. When x is equal to 0, it'll then pop up. So keep in mind, every time you know your x value and you're looking for your y value, we're just going to hit second trace 0 and then, or second trace and then plug in your value for 0. Let's try the next one. It says, use the model to estimate the birth year after 1900 that gives you a lifespan of 79 years. So right now, we know y is equal to 79 years. What we don't know is your x value. When does that occur? So in order to do so, we can set it up as 79 is equal to your equation, 82.488 divided by 1 plus 0.816 e to the negative 0.024 x. So graphically, we set them equal to each other, and then we can use them to intersect. So if we have two intersecting lines, so y1 is in your equation, y2 is the y value that we know. And when we go ahead and hit graph, we should have two lines. Now we want to know specifically where they're going to intersect. And if you're not seeing that intersection, or if you're confused as to where it might lie, we want to be able to adjust your window. So notice that I don't know definitively where it's going to cross, so I need to get a little bit further out, which means I'm going to be changing my x max. Let's do 150, graph it, and we can definitely see it comes out the other side, so your intersection is somewhere in the mix here. So let's go ahead and hit second trace. Value we said was when we know your x value. 0 we said is when you need to know your x intercept. We don't have a max or a min, but we do have an intersection.
New lyrics. Nationwide helps financial professionals identify their clients' long-term care needs.
So to intersect, we're going to find the left bound of where we believe the two lines meet. So to the left of that, and then again to the right of where we believe that intersection is. We can certainly tell that at this point to the right-hand side, the lines are coming apart. And then give it a guess. And it says that when y is 79, the intersection is at 121.5. So rounding out, because we're talking about a year, so this is about 122. So are we talking about the year 122? No, we are not. What year is it? Well, if x is equal to 0 for the year 1900, what is x, or what is the year when we are 122? Well, to find that out, we can just add 1900 to 122, which we get 2022 is our year. So this is graphically, if you did do it in Desmos, sometimes it is a little easier when you graph those lines to find that intersection. We're just clicking on the graph and then finding the important location of the intersection. Now, let's say you wanted to do it algebraically. The process to it is the same each time. So you set it equal to each other. Now keep in mind, when we punch it into the calculator, usually we put parentheses around the bottom. We do this because it is a whole unit that you would have to move, or that is together. So if our X value is located on the bottom in our denominator, we need to bring it to the top. How do we do that? Well, we're going to do it by multiplying both sides by your denominator. Now, again, I said this is going to be the same exact process over and over and over. Now, once you have multiplied it to one side, let me just copy so I don't have to write it again. It cancels out with one side and you throw it over to the other side. So now you get to multiply. Okay, algebra tells you to do what next? Well, you can go ahead and distribute that 79 if you want it on both sides. So we can go ahead and multiply 71 to this value. 79, so sorry, to 1. And then 79 times 0.816, which then becomes 64.464 e to the negative 0.024x. We're just multiplying those coefficients out front. You still have an 82.488 on the other side. Now keep in mind, we are trying to get this x to stand alone. So what's the next easiest thing that we can do? It is not going to be division. Always save division for the very end. Instead, let's go ahead and subtract 79 from both sides. Get 64, 46 more, and we can go ahead and do that subtraction. And now we can go ahead and divide. 64 for 64 is just the coefficient of e for right now. We're getting closer, believe it or not. Okay, now how do we get rid of e? Well, to get rid of e, we can either swoop or take the ln of both sides. I'm a huge fan of writing ln on both sides to show that they cancel, right? We have that hidden e that cancels and allows this to drop. So you have negative 0.024x is equal to the natural log of this value. Last but not least, we can go ahead and divide. Now you do not need to do this by hand unless you want. The process is the exact same every time. So as long as you're multiplying, adding or subtracting, dividing things properly, you're going to get to the answer no matter what. And when we plug it into your calculator, we'll get the year 2022. Or that is the year. X here will come out to be 1.5 or about 122. And there you have it. That is your X value. So again, big takeaway here, being able to punch these values into your calculator, figuring out what your limiting value is, and figuring out what a good window would be.